Here's the simplest way I can explain quantum tunneling and why it just won the 2025 Nobel Prize in Physics. Imagine throwing a ball at a wall. It bounces back. If it somehow appeared on the other side, you'd freak out. In the quantum world, tiny particles can do exactly that. They can tunnel through barriers instead of going over or around them. Not because they're cheating, but because in quantum mechanics, particles act like waves. Waves can extend into places they're not allowed, and sometimes that tiny extension lets the particle pop out the other side. That's tunneling. Now the big news, the Nobel Prize in Physics 2025 went to John Clark, Michael H. Deverett, and John M. Martinis for showing this tunneling effect in a circuit you could hold in your hand, and for revealing that its energy comes in chunks, or quantized levels. They built special superconducting circuits, materials where electricity flows with zero resistance, and use them to make a macroscopic system behave like a single atom. Same rules. Quantized energy. Real tunneling. Step by step, here's what they pulled off. 1. Cool the circuit so it behaves quantum mechanically. 1. Shape the circuit so it has a barrier like a hill in an energy landscape. 1. Watch the system jump between energy states by tunneling through that barrier, not climbing over it. 1. Measure the energy levels and see they're discrete, like a ladder, not a ramp. Why is that huge? Because it proves quantum behavior isn't only for tiny particles. It can show up in engineered devices made of trillions of atoms if you control temperature, materials, and design. That idea is the foundation of today's superconducting qubits, the tech behind the highest performance quantum computers from teams at places like Google, IBM. If you've heard of quantum supremacy, that landmark experiment used qubits, based on the same principles Martinis helped pioneer, and it's not just computers. These circuits enable ultra-precise sensors, help with low-field MRI, and push measurement science to detect incredibly faint signals. Here's a friendly analogy. Think of the circuit as an artificial atom. The energy comes in specific notes, and the tunnel is like a hidden passage between them. The weirdness you expect only in the microworld shows up in hardware, on a lab bench. So, what's the takeaway you can use today? Quantum tunneling isn't a sci-fi glitch, it's a reliable tool. We can scale quantum effects into devices you can hold. That opens the door to faster computation, sharper sensors, and new tech we haven't imagined yet. Quantum tunneling went from a textbook oddity to a hands-on technology, good enough to win the 2025 Nobel Prize. And that's why it matters. Congratulations to John Clark, Michael H. Deverett, and John M. Martinis, 2025 Nobel laureates in physics. Want more simple science? Subscribe for weekly explainer videos, sources in the description.